Good morning, wherever you are in the world. My name is Osvaldo Bascur. I will be presenting digital twin for low-grade mineral processing plant, and basically we're going to look into maximizing the net production rate. Is your flotation happy? Do you have enough water for processing the low-grade mineral? I'm working for OSB Digital and also a consultant fellow for SIG Advanced Analytics. Today's agenda will look at the mining sustainability in the digital age by looking at an integrated approach for production, waste, energy, and water integrated analysis. We're going to show what the digital twin concept is for processing low-grade ores. We're going to look into the dynamic decision support using hybrid process models and how to maximize the production of copper and the water recovery. And we're going to draw some conclusions. We started early on this, working on looking at the amount of energy that is required when you lower the grade to, let's say, 0.5% copper. The amount of energy is exponentially growing, as well as the amount of water which is required to process these ores. This is basically an integrated approach. We're using digital twins in the cloud. We're looking at the energy, water, uh, how the tailings are affecting the plant, and how this needs to be reshaped by using these new tools that are becoming available. We started very early working on this. This is me and Dr. Herbst in the 1980s, looking at how we are going to tackle these problems with using the latest technologies. And I was given the Antoine Godin Award in 2014, together with Dr. Herbst and Dr. Firstino, which has been good partners in coaching me and looking at the new ways of using the mineral processing theories and technologies. Usually, we can start from the mining and the mill integration, but also we are going to include today the tailings, because we need the water to process these ores. And we can start looking at basically the grinding, which starts at the blast, and how when the shovel is loading the truck, we can start thinking that that's a good disturbance that can be minimized if there are some issues there, so we can proactively look on how we need to run the mill. That's something that we have been working, and this was implemented at ArcelorMittal in Quebec a few years ago with great success. Um, One of the things that we find is that people are working in silos, not allowing them to use the tools together and to be able to have a good way of presenting that information that is being gathered from the processes into management. So when this is solved by using the new tools, especially working in the cloud today, there is a lot of things that can be done that were never able possible to done before. So I encourage you to look into that with more detail and have one way of doing that. Too many silos, as we said, there are too many microcultures. Avoid the solution that we are going to be presenting today. So this is something that is not related to technologies on how people needs to be reorganized. So there are too many versions of the truth. So sometimes we put this in spreadsheets and they are not doing anything because we just see what happened and we don't know how to tackle that in real time to avoid problems and to get out of the constraints that usually are being detected by the system. Lack of information of true value for management. So this is where we need to develop ways to transform that data so we can use it and augment it using the aggregate models that we are going to be presenting. Sometimes planning data is not considered in the operational data. And this is very practical so we can really assess if we are in the plan or we are not there. The industrial plan is segregated from the enterprise operational support. So there decouple, and this operation and the decision support needs to be integrated. So we are all working with the same type of information. It's very important. So this enables us to change or redesign the business processes. So operations and management and engineering and maintenance and the mining are all working together. So what is a digital twin? A digital twin is a computer representation of a physical integrated process capturing in real time the time series data and events. Events is very important. Those are the operating conditions in which each unit was operating, and we have to process the data into information and capable of simulating in parallel the behavior of the industrial plant, so we can understand what are the variables affecting the rare KPIs, which are in this case the net metal production rate, the size distributions, the rheology or percent solids and viscosity, and how those are sometimes very large issues in today's low-grade ores processing. And the plan is a set of unit objects which are communicating the information between each other to work in harmony, avoiding the constraint that might create major problems, so we can optimize if we are outside those constraints and minimizing the variability of those, so we can push towards the constraint in the system. So we take in mind here with their processing plant, their tailing ponds, and we integrate that into a digital set using this unit object and in an integrated perspective here using the PI system from OCSoft and now Aviva. So the digital twin in this case can be characterized by looking at the copper production in tons per hour, which is calculated by the tonnage, the grade, and the recovery. This tonnage is affected by the mineral, the rheology, the operation, the turbulence, and the water, and the assets availability, and the operating modes in which the comminution and the flotation and thickening are operating. The grade, of course, is coming from the mine, so that's where the cut-off grade and the management of the feed to the plant becomes very, very important. And the more we know about it, the better we can improve the processing of the low-grade ores. The calculation of the recovery is very important, and also we need to have the water being recovered correctly, so we need to understand how we can recover more water. So that's part of the discussion that we're going to have today. If we look at the typical recovery curve, which is the green line here, and the throughput, there is an optimal throughput, an optimal recovery, and this too is related to this net metal production. So this is very important. At the same time, we have found that sometimes we can push more the mill, but we lack of water because we are doing something wrong on the process that is not enabling us to have the right amount of water available. So we have to cut down on the throughput because not having the water. So we have to integrate that as part of the digital twin that we need to have to manage that correctly. So that's why we take the overall perspective of the mine, the tailing ponds, the processing plants, and how that water, which is recovered from the coarse material and from refined material, and how that one goes back into the plant to have that amount of water to be able to maximize the throughput and maximize the total copper production. So this can be represented by this diagram in which we have the low-grade ores coming into the plant. We got the amount of water that is being recovered and added to the grinding. We have the makeup water here, and of course the power to run the unit, all the units together. So by having this model of this unit-based environment that you are going to see, enable us to maximize the way that we are grinding, the recovery in the flotation, and the water. They are all affecting each other as we go through because the water comes back and we have that big feedback that is related to the thickeners and to the tailing ponds. So the data is something important here that we need to evaluate. It's dark data. If you have time series, they have to be processed correctly, sorting and cleansing, and adding the right context. So we have information to create the right analysis for continuous learning. And these systems are changing periodically, they are dynamically moving. When I present, for instance, a trend or a subset of the trend, usually we need to know how that data is being transformed into information. So here we use SIG tools which enable you to take that real-time data and transform it into analysis, which enable us to see what we have, develop the models, use the models that we have available, the mass balances, and so on, and be able to create dashboards which enable us to see where we are. I'm going to present a few of those as we go through. But having this analytical engine to tackle that real-time data and time series data is vital for implementing digital twin. So here we got the plant and we need to digitize it using this object. We got the rock processing at the front end of the plant, and then once we got the liberated mineral and concentrate, we can clean it. But the most important part is that we need to take the water out of the thickeners, take the water of the tailing pond, so we have enough water for the right efficient grinding here. The rheology of the grinding is very important, and also the rheology on how the thickener is being handled and how the paste that is created in the sands and in the slimes, those are critical for having the amount of water necessary to manage correctly the grinding, flotation, and thickening. So we need to build a data infrastructure that enables us to organize the data correctly so people can use it. They can identify the process unit constraint and be able to alert very early in time that those are not violated. And then we develop the predictive operational model using the dynamic models and the data. And then we identify and deploy the plant processes for optimization in a consistent way. So if we take the whole set, we have events which are characterizing the different processing effects which are connected with the process data. And those two needs to be analyzed, specifically the operating conditions of each of the units. So when we want to do a model, we take only the data that is in running mode and we compare to the one that was in trouble mode. So we know how much we can move towards the running mode, what the thing that we need to do to avoid getting into a trouble time where we are not going to get the base production that we are supposed to have. So this is basically where you do the analysis of the constraints, and then you put the water, the electricity, and you identify where are you making losses. And that's where you start tackling and trying to understand how to move away from those by predicting ahead of time when those things are going to happen. The most important area of the plant that usually is constrained is the cyclones. So the cyclone must create an air core to be able to separate the coarse particle from the fines. So they need to have the right percent solids or viscosity in essence. And this has been very well understood early on by Professor Lynch and Rao developed the first model which has been reused, and we have implemented better ways. Professor Muller has did a lot of work on that too, so we are incorporating some of those things in the real-time augmenting of the data of the cyclone using the real-time data. So here we have some of the experiments that we were done to characterize sulfite ores. Here you can see that 77% by analyzing this in a compression cell, we can identify that really the ore doesn't move. And this is usually what happens in the mills and the cyclones. So we need to be very careful on respecting these rheological conditions so we have an efficient grinding, an efficient size separation, and efficient thickening. We use this model which are characterized by being supervised or unsupervised learning. The state is very crucial here because that's how we can agglomerate and classify the different clusters of data that we use to parameterize the model and to understand what's happening in the plant. We also use some filtering to reduce the noise and things like that. So we have real information to understand the way that the plant is running. And this could be another talk, but I'm just going to leave it very simple for today. This is basically a result which is called Dynamil, which is a dynamic model that was developed, and now we're just parameterizing it and using the equations to augment the data that we have with information and looking at variables that sometimes are very hard to understand, but now by having the model it becomes easier. Here we have the net method production compared to the plant, so we are always like to be in a black mode, not in a red mode. You can see here that there are some constraints that have been at the edge of where they need to be, and this is really has been a tremendous change because now the mill is running much more stable, so that it helps for the flotation. And the same product, if you think, everything that we are grinding here goes to the thickening. So whatever the ball mills are doing here are going to the thickening. So by having the right size distribution, which is what we are modeling here with this size distribution with the D max, and which is the Coden, Schumann size distribution, we take those size distribution, we process them, we put them into the models so we know where to do and what to do, where to add the water, how much to add the water, so we have the size distribution that we need for the best flotation and for the best thickening. This is the model that is predicting the particle size distribution, as you can see here, and we model it so we understand what are the manipulated variables which are affecting the size distribution. And that's key to be able to maximize the recovery and to maximize the recovery of water. These are some of the variables just for you to have a feel of the data. The virtual sensor, which is the augmented size distribution, the target variables that we are managing, and then the control variables, which are the one that we want to have a closed loop. So these are the ones that we are going to be affecting the size distribution, the percent solid, and the size distribution. Again, the flotation is taken from the work that we did at the University of Utah in collaboration with UC Berkeley, and we do have this dynamic float, which characterizes the pulp and the froth correctly, so we can manage that and understand what is the best air flow rates that we need, what are the levels that we need in the bank. I'm going to show that with a little bit more detail here. So we are managing the turbulence correctly, we're managing the velocity and the froth to come up with the right KPIs for the flotation. So when we do the mass balance, we can see what is the best combination of these variables in the flotation bank, like you are going to see here. What is the best combination of these sets of possibilities to maximize, again, the amount of copper that is coming out from this rougher flotation. The tail that goes here, you're going to see, goes to the thickener. So basically, whatever we are grinding goes through flotation and they go through the thickener. So that's why we need to maximize the throughput in the mill by maintaining the right rheology, getting the right size distribution so we can maximize the amount of copper. This is a model that has been generated using the SIC and the analysis. It's all clean data, classified data, clustered data, and we use the flotation model with the variables which are generated here to model this. And we have a function that can be understood, and we can understand what are the effects of the different variables for the type of ore that we are dealing with, and see what we need to move, what we need to maintain to really assess the profitability of the plant. This tells you here by just graphing this, the recovery versus the particle size. Clean means that it has been pre-cleaned and classified. This is cluster data, and you have here 3,050, 4,200, 5,000, and you can see here that when you are maximizing the throughput, you get a parabola. It's very easy to see with these graphs that are being used by SIC, that enable you to do that very clearly and identify what is the particle size that we need now, what is the percent solid that we need now, and by plotting this in real time, you can assess that, you can model that, and then move towards the maximum copper production. Now what we have found is that when we are pushing the material here, we need more water to get the right efficient grinding. So we have to understand how the thickening is happening here and how the tailings are reporting back the water that we need to have here, because we don't have enough makeup water in these plants. They are very, they lack of water, and so we need to augment as much possible of the recovery of water. This is a real-time assessment of you can see here all these units are running correctly, because here we have the different operating conditions, and that's why we are developing the model. We are tracking very carefully the size distribution from the input to the output, and then we are seeing the effect of the size distribution both in flotation and in the thickening. As you can see here, when we started, the typical number was 4,500 tons per hour. Now they're running, in this case, 5,000 tons per hour, and as we learn more, we are now running higher molds, which is a very important result, because now we've got about 6,000 tons per hour of recovered water just from the thickeners. And now we are going to look at the way that this pulp has been from the tailings. We are taking a little bit more water and more water from the tailing pond of the fines. This model started to be developed very early with John Herbst and myself working at Chino Mines. And of course, we are adding into it, and then we can maximize the water production, which is vital for low-grade ores. So what we have done is that we are trying to maximize the metal production of low-grade ores. We need to have a steady throughput that will allow maximizing the rougher flotation and water recovery from the tailing effluents. It's a big challenge due to the complexity of the process and the variability of the grinding operation. We use the PI system with the hybrid phenomenological models, DynaMill, DynaFlow, DynaThick, that are helping us to augment from the data using information, the characterization of the behavior of these units, all together by having this digital twin. And SIGIS enable us to quantify the hidden losses of the different operating modes for all the units of the plant, and develop the predictive model of the net metal production rate, particle size distribution, water recovery, and so on. DynaMill is to model the grinding classification, very careful the classification based upon the model that has been developed over the years. So now the new data workflows allow alert engineers and operators to reevaluate the grinding and water operation to foster cooperation in a harmony and not silos. This is something that is work in progress, and it's very interesting because people need to realize what's really happening. So the results are that the recovery improvement has been 40%, and then the water improvement has been at least 1,500 tons per hour, which allow for higher feed rate worth several millions of dollars. Now, the important thing is that this has been done through coaching, and this coaching enabled us to really get the people correctly using the new technology and adopting new business processes for implementing this in the reality. Now, the typical, architecture here is that we have the plan, we have the control system, that one goes to the PI system, and we put this model, data model, that using the advanced analytic of SIG enable us to calculate the predicted process mean rate, process constraint, metal production, and put that in the decision support for better planning and better decision, and defining the segment targets and command to have these tangible benefits that you can read here, like metal production, which is the most important one, water recovery optimization, lost time analysis, identifying which areas require more maintenance or less maintenance, have the predictive equipment analysis, having an overall production effectiveness, which is how fast and push everything, and go and take care of the equipment. Environmental compliance has been improved tremendously because we have the data and information to tell the government regulation what is going on in the plant and manage the energy and water much better because we know what we need to do to avoid the constraint, which usually are the ones that causes the losses of water and energy from the production waste. Integrated plant collaboration is vital, and then of course the improved planning and scheduling is what enables to manage the whole mill correctly. So the digital twin plant model uh, uses the data that is transformed into information by users at the desired degree of detail. The users need to understand, and this has been very challenging, but little by little they are retraining and helping each other, and that's very nice to see. Use of hybrid dynamic process model to increase the visibility of the unknown. Seek advanced analytics to offer dynamic decision support for the mining complexes by cleaning, identifying what are the minimums and maximum, identifying what are the optimal, and defining the real-time models that are predicting and assessing the manipulated variable, which becomes available to see the influence on these variables. Pi system and SIG synergy. This is very important to develop the Pi system for the SIG connectivity so we can use it in a very practical way by as many people as possible. And the organization has to adapt because they need to do a lot more analysis, and it's a new team that is really managing this. And we have that way we can improve the operational efficiency and sustainability for lower corporate rates. So people is really a big change, cultural change that makes new business processes that needs to be implemented by management. And then the use of technologies is where the people has to be getting the new skills to run them and to manage them. So this is a long-term project that needs to be started as soon as possible because this is the way to really manage and low-grade ores in our processing. So thank you very much. You need to contact me. These are my details. I work for OSB Digital and I'm a consultant for SIG. So thank you.